Fine. So let us start. So welcome to the first class of statics and dynamics. So this is the most awaited class, and most of the people actually feel that actually this is one of the tough topic, but ideally it's not so tough. So the basics that you need to understand clearly so that you will be able to solve any kind of problems that are going to come as part of this statics and dynamics. And also actually I would like to know that actually many people actually thinks that actually this particular topic you can keep it a choice, but ideally you shouldn't do that. Why? Because the questions, especially for the 10 marks questions, right? So those are actually part of the statics and dynamics. And also in the SI questions, wherein actually one question is given for 50 marks, in that actually ABCD parts will be there. In that actually, so UPSC actually mixing the topic with other topics. That means if you leave this particular topic as choice, then there is a possibility of definitely losing the marks both in the 10 mark section as well as in the essay type question section. So that's why I strongly suggest that actually don't leave this particular topic. And to be precise, this is one of the very, very small topics, but many people think that this is a big topic, but it's not really. This is a small topic. If you notice, the syllabus is very, very small. The concepts also very, very small, but the number of models that you may have to practice is more. Got it? Fine. So now actually let me list down the syllabus what UPSC has published. Then actually we will discuss one by one. Got it? Okay. So rectilinear motion. And then simple harmonic motion. Rectilinear motion, simple harmonic motion, motion in a plane, projectiles, constrained motion, work and energy, conservation of energy, Kepler's laws, orbits under central forces, orbits under central forces. So this is part of the syllabus for the dynamics. And for statics, equilibrium of rigid body, equilibrium of rigid body, equilibrium of system of particles, work and potential energy, work and potential energy, friction common catenary, okay. So I just repeat, so this is the part of this syllabus what UPSC has published. If you notice, the syllabus is categorized into two different sections. One is the dynamics part. So till this point it is the dynamics part, and then the remaining syllabus is the statics part, right? And here actually the rectilinear motion, simple harmonic motion, motion in a plane, projectiles, constrained motion, work and energy, conservation of energy, Kepler's laws, orbits under central forces. So this is the part of the dynamic syllabus, right? So here actually if you notice carefully, this rectilinear motion, meaning motion of a particle in a straight line. So actually to study the particle motion, there are different ways. So you can simplify the motion of the particle into one-dimensional, two-dimensional and three-dimensional. So here one-dimensional motion is nothing but the straight line motion. The straight line motion can further be classified as straight line motion in a one-way and straight line motion in two-way or oscillatory motion. So together we can still treat as one-dimensional motion, that is the rectilinear motion and the simple harmonic motion are nothing but one-dimensional straight line motion. Maybe forward or maybe backward or maybe oscillatory on the straight line. So this is one-dimensional motion. And then motion in a plane is nothing but the particle motion under a plane. So if there is a plane, the motion of the particle is analyzed. So usually if you throw a projectile, the projectile is traveling in a parabolic path, but still even though the particle is traveled in a space, you will still treat that as a planar motion. Why? Because if you throw the particle like this, let us say, so you are throwing the particle like this. If you consider this vertical axis as the y-axis and this parabola direction as the x-axis, this is going to be a two-dimensional motion. So x direction and the y direction. You don't need to treat the third dimension. If you throw the particle in this way, so this is x-axis and this is y-axis, still it is a two-dimensional motion. So the motion of the projectile will still treat as the planar motion. So there are two different dimensions we were talking about. So those two-dimensional analysis we are doing, that is as simple as analyzing a parabola in case of mathematics. Got it? So this is a parabolic motion is nothing but the planar motion. So that is treated as the projectile motion. And the motion of the particle in a circle, that is also a plane. So the particle is traveling in a circular motion. So there are two different dimensions that are associated for a circle because that is a planar shape. Still you can treat that as a planar motion analysis. So one-dimensional motion and motion in a plane, projectiles and constrained motion is also as part of the planar motion we will be analyzing. So one-dimensional motion and two-dimensional motion. That's over, right? And then actually this constrained motion is nothing but you are constraining the particle to travel in a specific direction. You are constraining. Suppose actually, so you tie up a thread to a stone and then you try to rotate that. Now actually you are constraining the particle to travel in only in a circular motion because you are holding the thread. So hence actually that can be treated as a constrained motion. And take one more case. Suppose let us say you are in a spherical shape. So a closed shell is there and within that you are there. And you are throwing a stone on the surface of the sphere. Then you are constraining the particle again to travel in a spherical shape or a circular shape within the shell. So there also you are constraining the particle to travel in only one particular way. That is the kind of analysis what we are going to do as part of this constrained motion. So maybe actually when you are throwing with a thread to a stone, then actually let us say there is a pin and that pin actually it is suddenly caught. Then actually it will try to rotate about that particular pin. So that also you can treat as a constrained motion and then actually we will be analyzing the constrained motion. Still it is a planar motion. So planar and constrained. So that is the kind of analysis what we are going to do as part of this constrained motion. And then work and energy. So work always comes with the energy, right? So because you have the energy, you are able to lift this chalk piece. So the energy and work both are one and the same. That's what we call that as the work energy theorem. So whatever the work we do, that will be converted as part of energy, or whatever the energy you consume, that is going to be used to do certain work. So that is how the work and energy are interrelated to each other. So work actually is a necessary component that is needed for a particle to move from one location to another location. So you have to do certain work, then only the particle is going to move. Suppose actually I am lifting this chalk piece. If I am lifting this chalk piece, which essentially means that I have consumed my energy to move the particle from one location to another location, and moving the particle is called as the work. Whatever the energy that is going to be consumed is of mine. So my energy is consumed to do this work, and this work is resulted in moving the particle from one location to another location. So if there is a movement of the particle, there has to be a work that is going to be done. That is the result of the energy. So these two are actually coming together. So as we are trying to analyze the particle under motion, the work and energy are the necessary component which will result in some force. The force indirectly results into the moment, right? So that is what we are going to analyze as part of this work and energy. And then conservation of energy. So this is the basic principle under the physics, right? So physics always builds with this conservation of energy. This is a very, very basic principle. Suppose if you have invented some formula, let us say that formula is violating the law of conservation of energy, then there itself actually you can conclude that whatever you proved is wrong. So that is the kind of understanding this conservation of energy is having, right? So conservation of energy is nothing but, so energy can never be created nor destroyed, but it will change from one form to the another form. Suppose actually, let us say, so I got the energy as I am taking food. So the food energy actually whatever I have taken, and this is going to be converted into the potential energy for moving this chalk piece from bottom to the top. So there is a movement of the particle here, and this energy we are calling this as the potential energy. But this energy resulted just because I am having food. So that is the chemical energy whatever I have taken is converted into the potential energy. If I leave this chalk piece again, it is going down with certain velocity. Hence actually it is going to be associated with certain kinetic energy. So potential energy is getting converted into kinetic energy, but still whatever the energy I have used in lifting this chalk piece, the same energy is getting converted into the potential energy. The same energy is getting released in the form of kinetic energy. When it hits the ground, this is producing a certain heat energy. So the energy is actually changing from one form to the another form. So the energy can never be created nor destroyed. Then the fundamental question comes. Then where is the energy? Energy can never be created nor destroyed. But we are making use of the energy, right? So from where we are getting the energy? Can somebody guess? A wild guess? Where are we getting the energy? Because nobody can create. So as nobody can create, there has to be some way of generation, right? From where we can get the energy? It is going to be transformed, but somewhere it has to be there, right? It is going to be transformed from one form to the another form, that is there. But somewhere it has to be there, then only we can transform from one form to another form. Gravity. So gravity is there, and then actually whatever the food we take, it is coming from the ground, right? Whatever the fruits we take, right? So those are from the trees. If you notice, the oil and natural resources, everything actually, it is coming only from the nature. So nature already has energy in one or the another form. Nobody can create it. Nature only can create it. So nature created that energy. That energy we are making use to transform from one form to the another form. In this process, we are trying to make use of that energy as per our convenience, as per our requirement. So the energy is there in the nature itself. That energy we are making, and this is limited energy. So if you notice, actually most of the wars between the countries are happening just because of the crude oil. So because that crude oil or that petrol or natural gas, everything is limited and it is produced by the nature itself, nobody can create, or no human can create any form of energy. So the nature only creating the energy, that energy is fixed quantity. That's why we are actually making wars just to capture that energy from one country to the another country, right? Because this is limited. So this is the basic principle that is behind most of the wars. So law of conservation of energy, because energy can never be created nor destroyed, right? And then actually the Kepler's laws. So these Kepler's laws are actually the basic laws which are used to analyze the motion of the planet. So planets are actually already associated with certain form of motion, certain form of path, so certain form of orbits. So those orbits actually how they are formed and what is the kind of motion that a planet is having, and then what are the rules behind the planet motion. All such kind of analysis are the first postulated by this Kepler. So this Kepler's laws actually we are going to analyze. If you notice, this Kepler's laws is a subtopic of orbits under central forces. So this is a master topic. In that master topic, there is one particular case when the force of attraction is directly proportional to 1 by r square, then that kind of analysis we call that as the inverse square law. And this inverse square law is having certain postulates. Those are postulated by Kepler, and these are the motion. This is the kind of motion that is going to be associated for each of every planet, right? So this planetary motion is going to be analyzed as part of the Kepler's laws. And then orbits under central forces. Orbits under central forces meaning, suppose if you notice, let us say this is sun and then this is earth. This is trying to move around the sun, and then as per Kepler's laws, what it states is every planet tries to rotate in an elliptical orbit with sun as one of the focus of the ellipse, and this is the kind of motion actually it is going to be having. Now if this is the kind of motion, if you notice, the force of attraction always passes through a single point called the focus. Suppose let us say this is an elliptical path, and then this is the major axis and this is the minor axis, and this is one of the focus and this is one of the focus. Let us say the sun is located here and then the earth is located here. The force of attraction between these two, and that force of attraction is nothing but the Newton's law of gravitation. So any two different masses are always attracts each other. So sun is one mass and earth is another mass, and there is a force of attraction between these two. So these two are actually the mutual forces. Mutual force meaning, so the sun is attracting the earth is attracting the sun, but whichever is heavier, that will stay as it is. Whichever is having the least weight, that will come and attract each other. But if the sun is attracting this earth, if it comes and joins in this, then actually there is nothing like earth, because it is going to be collapsed. So to manage that, so that actually earth wants to protect itself. For that, it will try to move. So it will try to move in a path. That is what we call as, this is the orbit. So it is moving in an orbit so that it can withstand the force of attraction between the sun and earth. So it wants to protect itself so that it won't fall into the sun. Now this is a mutual force. Sun is heavier here and earth is having the least weight. So that's why actually it starts rotating, not the sun. So it is trying to rotate, and here there is a force of attraction between these two. Let us say the earth moves to this location. Still there is a force of attraction between these two. Suppose earth moves here and then there is a force of attraction between these two. If the earth moves here, there is a force of attraction in this particular direction. Now if you notice, wherever the earth is located, this is always passing through a single point. This is always passing through the sun itself, and this single point is the force of attraction. So in all the direction actually it is having the force of attraction, and that line of force always passing through a single point. Such kind of forces are called as the central force. So this is the central force. So the motion under central forces is having certain rules and regulations. So if there is a central force, that we can be sure that the particle always moves in a planar, which essentially means that suppose this is the sun and let us say this is the earth, and then it starts moving in an elliptical path like this. Now actually we cannot think that actually the particle tries to rotate in this manner once, and then actually if it tries to rotate in this manner, and if it tries to rotate in this manner. So in all the sense actually it is having a three-dimensional shape, but the force under central forces, what it relates is, it will always assures that the particle moves in a single planar motion. That means it will always tries to rotate like this only. So it cannot move once like this and once like this. Got it? So that is the rules that is laid out by the Kepler. So this Kepler, so the Kepler has laid out the rules, and then this can be proved mathematically. The particle actually is moving only in the planar motion, that we are going to prove as part of this Kepler's laws. Now, under this particular case, if you notice, as per Newton's law of motion, so here, so F is directly proportional to mass 1 and mass 2 and inversely proportional to square of the distance d is 2. And then F can be treated as 1 by r square. Now, this is what is called as the inverse square law. This is what is called as the inverse square law. So, as and when we have a central motion, or as and when we have a motion under central forces, then this is one particular case, F is directly proportional to 1 by r square. There can be cases F is directly proportional to 1 by r cube also, and 1 by r power 4 also. So, in all such kind of motion, actually, if you notice, the force of attraction always passes through a single point. Hence, this is called as the central force. In that one particular case, is F is directly proportional to 1 by r square, from where actually we derive the Kepler's laws. Got it? So, this is what actually we are going to study as part of the motion under the central forces and the Kepler's laws. So, this is the short syllabus what we are going to have as part of dynamics. So, to summarize, rectilinear motion and simple harmonic motion is nothing but the single dimensional motion, and then planar motion, projectiles and the constraint motion actually we are analyzing as part of the two-dimensional motion, and then actually we are not dealing with the three-dimensional motion here. So, we are dealing with only two-dimensional motion and the one-dimensional motion, and three-dimensional motion actually we will be covering. So, though it is not part of our syllabus, we are not covering here, but in vector calculus when we deal with, so Serret and Freinet formula are related to the motion under the 3D space. So, there we are going to separately study the three-dimensional motion as part of Serret and Freinet formula, but that is not part of statics and dynamics. So, got it? So, there actually in vector calculus I am going to cover that. Now, here work and energy. So, here one-dimensional, two-dimensional, and the cause of motion is nothing but the work, and that cause of motion is work, and work is actually caused by energy, and these two actually will be studying. And then, so the conservation of energy is part of energy itself we are studying, and then Kepler's laws and orbits under central forces are nothing but the two-dimensional motion, the planar motion. So again actually it is going to be the planar motion, but it is in a elliptical motion. So this is the short syllabus we are having: one-dimensional, two-dimensional and energy. So three different topics are covered as part of the mechanics. Got it? So this is the syllabus what we are going to study as part of dynamics. So do you have any questions in this? Any questions? Got it? Okay. And then actually coming to the statics syllabus. So statics actually there are two different ways. So one is actually, let us say there is a chalk piece here, and then actually this chalk piece is associated with certain weight, and this weight actually always dragging towards the ground, but I am lifting with my hand, and whatever the weight it is having, if I could able to balance at this particular location, I can be sure that this chalk piece stays here itself. Suppose if my force is more than the gravity, then actually it is going to be lift upwards. If my force is lesser than the gravity, then it is going to down. So if it is exactly equal, then actually it is going to be staying as it is. So here, this is what we call as the particle under equilibrium. So here if you notice, there are forces that are acting on this body, but still it is not moving. So to summarize these two particular topics, right? So this is the particle under motion, this is the particle under stability or the particle under equilibrium. So here actually when we are analyzing the equilibrium, suppose actually let us say, if you notice, I am having a force on this particular chalk piece, and then actually it is trying to rotate like this. Now if you notice, the particle exactly on tip of my finger is not moving anywhere. So it is staying as it is, but this pen is trying to rotate. All other particles are moving from their respective locations, but the particle exactly at the center actually it is not moving to anywhere. It is trying to stay as it is there, right? Now here actually the fundamental question comes. Suppose if I keep the chalk piece like this, there are forces that are acting on it, but still actually it is not moving. None of the particles are moving. So this is what we call as the equilibrium of body. So this entire body is treated as a single particle, and this is staying as it is, hence actually it is under equilibrium. Suppose if I try to rotate, one particle is not moving, but rest of the particles are actually trying to move it. Now, when we wanted to analyze this pen itself, now you have to divide this pen into infinite number of particles, and then we have to assure that each and every particle under stability, each and every particle under equilibrium, then only we can be sure that this particle is not moving or this body is not moving. So there are two different kinds of ways actually we are going to analyze. One is the particle under equilibrium and the particles under equilibrium and the body under equilibrium. Body means this entire thing is treated as a single particle, and we have to assure that the particle is not moving. Suppose if you are treating as infinite number of particles and then you are assuring that each and every particle is not under motion, then you can be sure that all the particles of this body are under equilibrium. So there are two different kinds of ways we are going to analyze. In the first case actually, if there is a force and all the forces are compensating each other, then you can be sure that the body is under equilibrium. But when you are treating as each and every individual particle, here in this body itself, when it is trying to rotate, one particle is under stability, but rest of the particles are moving. That means if there is a rotatory motion, then actually you have to assure that each and every particle under equilibrium condition. For that, you have to assure that the torque is also zero along with the force. So the torque and force together, you have to make it zero, then only you can be sure that each and every particle of this body is under equilibrium condition. So those are the two different kind of analysis what we are going to do. That is, the equilibrium of rigid body is essential, means that you are treating the entire body as a single particle, and then equilibrium of system of particles, all the infinite particles of this body are nothing but the system of particles. Now this system of particles actually we have to assure that under equilibrium condition. So that is what we call as the equilibrium of the system of particles. And then work and energy and the potential energy. So work and energy, as and when there is a motion, or actually as and when actually this body has acquired certain energy, though it is staying at this particular location, it is still associated with its potential energy, because there is a reference of ground. So from the ground actually it is at certain height, then actually it has got certain potential energy. So that energy we are going to calculate as part of this statics. So work and potential energy. And then the friction. Friction is nothing but, there are two different kinds of frictions. One is the static friction and there is the dynamic friction or the kinetic friction. Now here, suppose if there is a body like this, now when we try to move it, then actually if I apply very very small force, there is a force that is acting on this body, but still this body is not moving. Suppose if I increase my force, then it is about to move. If I further increase, then actually it is going to move. So here actually there is stability of this body at this particular location, though I am applying a small force. That means that small force is not sufficient to move this particular particle. There is, suppose this is the ground and there is a body on this. Now here actually there is a force that is acting, and this F1 is very small, let us say. If it is very small, this body is not moving, but there is a force acting on this, then there is a compensatory force that is going to be developed exactly equivalent to F1. So the compensatory force is going to be developed here. Now if you still increase the force, this compensatory force also is going to increase. Now if you draw a graph, let us say, now here actually, let us say this is the frictional force and this is the force what you apply. Now if you keep on increase the force, the friction also keep on increases to some extent. Now at one instance, the frictional force is getting compensated by this force, and this force is having extra force. Then actually it is going to drop and then actually move like this. So here actually, let us say if you take the simple example, we are trying to push the car. Now before the car starts moving, when we are pushing, we need to apply more force. Once the car starts moving, then actually you feel easy. That means actually lesser force than what you have applied is sufficient enough to move once it got started. So this is the force that you are applying. So this is the topmost force what you are applying to make the car move. Once it starts moving, you don't need to have that much of force. So this is called as the kinetic friction. So this is called as the static friction. And then this is called as the dynamic friction. So this is the static friction and this is the dynamic friction. Dynamic friction is always lesser than the static friction. So here actually, from here to here, you are applying the force, but actually it is not moving. And here actually the car starts moving, you apply the force, and whatever the balance force that is going to be used to accelerate this particular car. That means when there is an acceleration, there has to be a force. That force actually will result in moving the particle from one location to another location. So till this point it is under stability and then it is not moving, though the forces are acting on the body. Once it starts moving, there is a motion of the particle. Now the relation between statics and dynamics exactly comes here. So here, when there is a force that is acting, if the particle is not moving, then actually we say that the particle under stability or the statics or the equilibrium condition. And the same force, if it results into the movement of the particle, then we analyze that as the dynamics. So these two topics together we call as the fundamental topic called the mechanics. So mechanics actually, so this can be defined as force and its effects. So force and its effects we analyze as a single topic called the mechanics. In mechanics, there are two different subtopics. One is analysis of the particle under the influence of forces. When the body is not moving. And this is called as the statics. And here the analysis of the body under the influence of forces when the body is under motion. So this is what is called as the dynamics. So in both the cases actually what we are trying to do is, we are trying to analyze under the influence of forces how the particle is behaving. Suppose let us say this is the particle or this is the body, and then actually it is having certain weight and the mass is m. So this is having certain weight. Let us say there is a table like this. On the table actually this body is there. Obviously there will be its normal reaction which is exactly equal to this mg, and then n equal to mg. If this is the case, then actually we can be sure that this particle is not going to move. But there are two different forces that are acting on it. One is the weight and another is the normal reaction. So these two together making the body under equilibrium condition. Equilibrium meaning even though the forces are acting, if it is not moving anywhere, then we say that the body is under equilibrium condition. So this is exactly the case actually. The body is under equilibrium condition even under the influence of the two different forces. So this is called as the statics. And suppose if I take the same body, but I am externally applying a force on this, and there will be a little bit of friction, then this is my force. So I have the flexibility to apply more force or lesser force. But this is influenced by the frictional force, or this is nothing but the ground or the rough surface. And then F minus small f is the effective force that is acting on this particular body. So this is my force, this is frictional force, and the difference of these two is more, or actually it is having certain positive value. Then actually this will start moving in this particular direction. So this is, as the particle is moving under the influence of the force, definitely it will be associated with certain acceleration. So here F minus F is nothing but ma. So ma is equal to F minus small f. And here the particle is associated with certain forces and it is having certain motion. So this is what we are going to analyze as part of the dynamics. So this is the fundamental. So here where we start analyzing this particular topic, the statics and dynamics. So in both the cases, if you notice, there is a simple concept, that is the force. So the force is having certain properties. So force, actually, the properties of the force are, first is the magnitude of the force. And the second one is the direction of the force. And third one is line of action of the force. So these are the three fundamental quantities or three fundamental characteristics of the force which will have a lot of effects on the body, right? So these three fundamental. So here, actually, suppose if there is a body like this, when you are applying the force, now here, actually, when we are applying the force, you say that 10 newtons of force is acting on the body. That means you are associating certain number, which is nothing but the magnitude of the force. So this is F, which is nothing but the magnitude of the force, let us say 10 newtons. And then you are saying that there is a force that is acting on this body from left to right. Now left to right can be here, can be here, can be here, can be here. So in all the cases, actually, left to right is the force that is acting. Now, one more important characteristic that you need to identify is the line of action of the force. Now, on this body, where exactly the line of action of the force is passing through. So that is what is very important to have the effect on the body in different manner. For example, suppose if the force is acting exactly at the middle, then actually it is going to have a linear motion like this. But suppose, let us say this is the body, and then force is acting at the top, then actually due to the frictional force which is acting opposite direction to the force, it will try to topple or it will try to rotate rather than moving. But the same force. So here it is causing a linear motion, but here it may cause a rotatory motion depending upon the line of action of the force, or actually depending upon the point of application of the force. So these are the important characteristics of the force which is having influence on the body in different manner. Got it? So this is what we are going to analyze as part of statics and dynamics. Got it? And then common catenary. So common catenary is nothing but, suppose actually if you see a telephonic line or an electric pole, right? So between the two poles, so let us say this is one pole and this is another pole. There is a wire connected between these two. Now, due to its natural weight, it is going to associate with certain sag. Sag is nothing but coming from the exact location to a little down due to its weight. So, this is having certain sag. And then, what is the kind of shape it is going to come due to the weight, as the weight is continuously distributed across. And then, this is where actually we are analyzing the sag, and then what is the minimum height, and what is the force that is acting at this point, what is the force acting at this point, and what is the force that is going to act exactly at the middle or wherever you want. So, analyzing the string which is connected between two different poles is nothing but the common catenary. So, there actually we are going to analyze the sag and the force at different locations. So, that is the common catenary. And then, principle of virtual work. So, this is actually one of the technique that is going to be used to identify or to know the unknown force magnitude. So this is one physics principle. So the principle of virtual work is nothing but, so if the body is under stable equilibrium, so equilibrium having actually two different aspects again, stable equilibrium and unstable equilibrium. Now actually I am going to explain a little about it. See this, suppose, see this, let us say I am going to balance this pen like this. Now this is under equilibrium condition now because actually this is not moving anywhere. But let us say if somebody pushes a little bit like this, then actually immediately this is going to fall down like this. So little bit of force acted on this, even though the body is under equilibrium condition, the small force is causing the body to move away from its equilibrium condition. And this is called as the unstable equilibrium because the body is under equilibrium now, but if I apply a little force, it is going unstable. So this is unstable equilibrium. Suppose if I take the body like this, let us say I am holding like this. Even if you apply a small force on this, it is going to come back to its original position. And this is what is called as the stable equilibrium. So there are two different kinds of equilibrium, the stable equilibrium and unstable equilibrium. Now, if the body is under stable equilibrium, then if you give a little bit of displacement, and this displacement is called as the virtual displacement, because even if you give the displacement, it is going to come back to its original position. Now, in this particular course of action, you have given certain energy, that is what we call as the virtual work you have done. You have done certain work, but the work is reverted back. That means essentially we have done zero work. Even if you give it, it is going to push our body again backwards. That means you are giving essentially zero work, which is nothing but the virtual work. So by giving a virtual displacement, by applying the principle of virtual work, that is the effective work done equal to zero, then with this understanding, if there are forces that are acting on this body, you will be able to know the unknown force magnitude with this understanding of principle of virtual work. So, got it? Right? So that's what actually we are going to study as part of the principle of virtual work. And then stability of equilibrium. So this I have already explained. The equilibrium can be stable and unstable depending upon the type of equilibrium it is going to have it. So that is the stability of equilibrium. And then forces under 3D. That means suppose if, let us say, if I take this particular body, there is a force acting downwards, that is nothing but the weight of this body, and there is a force that is acting upwards, which is nothing but the normal reaction of this body, and these two together actually is making the body under equilibrium condition. Now here actually, if you try to notice, we are trying to analyze only the coplanar forces. Coplanar forces are nothing but the forces acting on a plane. So on a plane, let us say if you take the wall, on the wall actually the forces are acting, then actually that is going to be the coplanar forces. But if you take the beam which is in a space, now actually there are different kind of forces. Suppose actually if I take, let us say the forces are acting like this. So this is one force, this is one force, and this is another force. Now all the three forces are in three different directions which are perpendicular to each other. Now here actually you cannot do the analysis of coplanar forces to identify the equilibrium of the body under three-dimensional, because one force is trying to push in this manner, one force is trying to push in this manner, one force is trying to push in this particular manner. Now there are three different forces but three different directions. But suppose actually if I have a force like this, suppose actually let us say I am trying to push this like this. So there is a thrust on this pen in this direction, there is a thrust on this pen in this particular direction. Now actually here actually on the same line of action actually the forces are acting. Now on the same line of action, that is, let us say this one. Now there is a force on this and there is a force on this. Now in this case actually the line of action of the force is same. Now in this case actually you will be able to analyze easily because the vectors are on the same straight line. Suppose now there is a force acting on this, there is a force acting on this, there is a force acting on this. Now actually it's not on the same line of action of the force, but all the forces are actually on the board itself, that is nothing but on a plane itself. Now all these three forces together, this is F1 and this is F2 and this is F3. Now as long as you can be sure that F1 plus F2 is equal to F3, then this body is under equilibrium condition, though under the coplanar forces, right? And then the next one is the three-dimensional forces. Suppose this is the block. So let us say this is a 3D shape. On this 3D shape, now if there is a force acting on this, if there is a force acting on this, and then if there is a force acting on this, then three different forces in three different directions that are acting on it, and these three forces are not the coplanar forces. In such cases actually you cannot make use of the analysis of coplanar forces, because the coplanar forces analysis is very easy, as you can make use of the parallelogram law of vector addition or the triangular law of vector addition, but in this case you cannot make use of it. So the body actually under this particular condition is a little bit complexity that is going to be involved to analyze this kind of forces. So here actually the forces under 3D are going to be treated as separate topic, because the complexity goes 3 times, not the double, 3 times it goes. So because you need to analyze these two, you need to analyze these two, and you need to analyze these two. So different combination of the forces that you are going to take it. Hence actually a little bit of complexity that is going to be involved as part of this non-coplanar forces. This topic we separately analyze it. Got it? So this is the entire syllabus of statics and dynamics as part of UPSC mathematics. Got it? This is one of the very important topic, because the questions are going to be mixed with the different topics. Hence you cannot skip, or you cannot keep this as the choice. So all these questions are actually the compulsory questions, because there are questions for 10 marks and there are questions even for the mixing with other essay type questions. Hence you cannot afford to leave it. So if you afford to leave it, then actually essential means that you are not able to qualify mathematics, at least for the year what you are writing, because the involvement of the questions are more. Got it? Any questions on this? Any questions? Okay. So the books that are going to be followed. So I think so we have actually only one set of books, that is the statics book and dynamics book both by Krishna series. So these are the books I follow, and actually I didn't find any other book also, because these books actually exactly follows UPSC syllabus. Hence, and more number of models are going to be covered in this. So hence actually I ask you to buy only these books and then follow from these books, and I will be teaching only from these books. Got it? Any other questions? Right? Okay. So if there are no other questions, I am going to log out of the class. So please let me know if you have any questions, or you can post in the group. I will respond for that. Fine. So the classes are going to be continued at 10 a.m. till the lockdown gets over. So after the lockdown, actually we may shift the timings. But till then, actually, as everybody is at home, then everybody can attend the classes in the daytime itself, though you are working. Got it? And then actually Sir actually will resume the classes within 2 days, and then actually these two classes are going to run in parallel. Yeah, so that's all for today. Yeah, thank you. Bye bye.